In this video, we will look at algebraically evaluating double integrals. So the question becomes, how do we evaluate a double integral? And we should first look to the definition of the integral to give us a hint on how to evaluate these double integrals. So a double integral over a region R of f of x, y, dA is in fact the limit as m and n go to infinity of the sum from j equals 1 to m, and then the sum from I equals 1 to n of f of x sub I, y sub I, delta A. But we can think about delta A as being delta x times delta y. And then, if this double sum is finite, we can think about this double sum as being the sum from j equals 1 to m of another sum of f of x I, y I, delta x. So we can add some parentheses to help us get a sense of the order in which we're going to evaluate this sum. Well, then I have a limit as n goes to infinity of a Riemann sum delta x on the inside of these parentheses. So I can rewrite this as the limit as just m goes to infinity of the sum from j equals 1 to m of, and then inside the parentheses, I would have an integral, say from a to b, because that's the limit of that Riemann sum, of f of x, y sub I, dx. And of course, I'm taking that sum delta y. Now, what is on the inside of these parentheses right here is a function of y. And so what I really have is a Riemann sum of a function of y delta y. And so that too can be thought of as an integral. And so I can think about this as the integral from c to d when I take that limit as m goes to infinity of the integral from a to b f of x, y, dx, and then I'm going to integrate that again, dy. And so what we have inside the parentheses is an integral that we perform dx, and the result is a function of y. And then outside the parentheses, we have a function of y that we're going to integrate dy. So this integral above is called an iterated integral. Now, I've made some assumptions here that R here is really not just a general region, but say a rectangle. So it's the rectangle AB in the x direction, and then C to D in the y direction. But we can actually do the same sort of thing for more general regions, which we will address in the next video. But essentially now, this gives me a technique for evaluating double integrals. And that is to look at the inner integral, dx, evaluate that integral, and then evaluate the outer integral, dy. So let's look at an example. We want to evaluate the integral from 1 to 2 and then 0 to 2 of x minus 3y squared dx dy. So I've actually drawn the region that we're going to integrate over to the right. Okay, so we're going to integrate from 0 to 2 in x, and you'll notice that this rectangle goes from 0 to 2 in x, and then we're going to integrate from 1 to 2 in y, and you'll notice that the rectangle goes from 1 to 2. So our region of integration is in fact the interior of this rectangle. So now I want to evaluate this integral. So the way I'm going to think about it is this is the integral from 1 to 2 of, inside in parentheses, the integral from 0 to 2 of x minus 3y squared dx, and then I'm going to evaluate that dy. Okay, so on the outside I have an integral from 1 to 2 that is being performed dy. And then I want to look at what's on the inside. So I'm going to integrate x minus 3y squared dx. So the antiderivative of x is 1/2 x squared. And then the antiderivative of 3y squared, well, that's just a constant. So we're going to just multiply that by x. So this is going to be 3xy squared. And I need to evaluate that between 0 and 2. So I'm going to integrate from 1 to 2. Now I'm going to evaluate what's on the inside of those parentheses. Okay, so 1/2 x squared. If I plug in a 2, that becomes just 2. And then I'm going to subtract. If I plug in a 2 for x into 3xy squared, that becomes 6y squared. And then I subtract the same thing evaluated at 0. But you'll notice if I plug in 0 for x, I'm just going to get 0. So I'm just going to leave that alone there. And I want to integrate this dy. So now y is my variable. The antiderivative of 2 is going to be 2y. And the antiderivative of 6y squared is going to be 2y cubed. And I want to evaluate that between 1 and 2. Well, that gives me, let's see, 2 times 2. Minus 2 times 2 cubed, and then minus plugging in y for, or 1 for y, we're going to get 2 minus 2. So in fact, I'm going to get 4 minus 16, which is a negative 12, minus 0 there. So this integral, this double integral, evaluating it in this way, we get negative 12. Now, I made a choice when I did this integral, and the choice that I made here was that I would integrate with respect to x first and then y. Okay, so essentially, when I rewrote this double integral here, when I rewrote delta a, I wrote it as delta x, delta y, and I did the sum for the x's on the inside and the sum for y's on the outside. But I could have done it the other way. I could have written it as delta y, delta x forms delta a. And then I could have done the sum for the y's on the inside and the sums for the x's on the outside. So I would like to evaluate this integral dy dx, where y is the variable that I'll integrate with respect to first. And then we'll just see what happens. So I'm going to integrate from 0 to 2. And then I'm going to integrate from 1 to 2 of x minus 3y squared. And then dy dx. And I want to see what the result is. Okay, so this is an integral from 0 to 2 of, okay, so I'm going to integrate the inside dy. Okay, so what am I going to get? Well, the integral of x, which is just a constant dy, that's going to be xy. And then the integral of 3y squared, that antiderivative, is going to be y cubed. I want to evaluate that between 1 and 2, and then that whole thing is going to get integrated dx. Okay, so let's see what this looks like. So it's the integral from 0 to 2. Now I'm going to substitute in some numbers for y. So I'm going to get 2x minus 8. And then minus, and when I substitute in 1, I'm going to get x minus 1. Integrating all of that dx. So now this becomes the integral from 0 to 2 of 2x minus x becomes x. And then negative 8 plus 1 becomes 7. So I'm going to integrate that dx. Okay, so the antiderivative of x is 1/2 x squared, and then minus 7x. And I'm going to evaluate that between 0 and 2. So that's going to give me 1/2 times 2 squared minus 7 times 2. Okay, and 2 minus 14 is indeed negative 12. And so you'll see when I integrate over that same region, but now I have the integral dy dx, I also get negative 12. Okay, so thinking about that double sum as the inner sum being delta x and the outer sum being delta y, that's no different than thinking about the inner sum as being delta y and the outer sum as being delta x. So in fact, this is a theorem. Okay, let f of x, y be continuous on a rectangle AB by CD. Then let's see, if we integrate f of x, y, dy, dx, notice that the y corresponds with c to d. Okay, the x corresponds with a to b. Then that is going to be the same as if I do the integral from c to d, then the integral from a to b of f of x, y, dx, dy. So here, notice that the outer limits of integration always match the outer dx or dy, okay? And then the inner limits of integration match the inner dx or dy, okay? So we have a sense switch the order of integration, but we are going to get the same result, okay? This is a theorem due to Fubini. And the way that you would justify that, and I kind of alluded to earlier in the video, is that you'd use the definition and then you would switch the order of the finite sums before taking the limit. And as important is that the sums in this case must be bounded for this to be true. They can't be infinite. If the sums are infinite, then this does not work. Okay, so the sums must be bounded for this to be true. Okay, so that gives us essentially two methods to evaluate a double integral. We can evaluate it first with dy, then dx, or we can evaluate it first with x being the variable and then y. Okay, I would like to do just a couple more examples. This is another double integral. It's the integral from 0 to 2, then 0 to 4 of x squared e to the minus y dy dx. Okay, so I want to evaluate this double integral. So it's the integral from 0 to 2. Okay, I'm thinking about y as being the inner variable there. So I'm going to integrate x squared e to the minus y dy. It gives me a negative x squared e to the minus y evaluated from 0 to 4. And then we want to integrate that expression dx. Well, let's look at that inner expression and substitute in for y. Okay, so we're going to get minus x squared e to the minus 4, and then we're going to get a plus x squared e to the 0. Okay, and we're going to evaluate that dx. I just want to simplify that just a little bit. Okay, so this is the integral from 0 to 2 of x squared times 1 minus e to the minus 4, kind of factoring out the x squared, and I integrate that dx. Okay, I'm going to notice that the 1 minus e to the minus 4 is just a constant. So when I integrate dx, that's going to be 1/3 x cubed times 1 minus e to the minus 4, evaluated between 0 and 2. And so that's going to give me, substituting into 8/3 times 1 minus e to the minus 4. And then I would subtract 0 when I substitute in 0 for x. Okay, so there is my double integral. But there's something interesting about this function, and that is that this function is x squared times e to the minus y. It's really a function of x times a function of y. And so because of that, I can actually evaluate these integrals separately, and I'll kind of show you how that works. I can look at just the integral from 0 to 4 of e to the minus y, which, if we find the antiderivative, is minus e to the minus y, evaluated between 0 and 4. So that's minus e to the minus 4 plus e to the 0, and that is 1 minus e to the minus 4. And then I can integrate x squared dx, and I'll notice that that is 1/3 x cubed, evaluated between 0 and 2. And then that gives me an 8/3 when I substitute in the 2, and then a 0 when I substitute in 0. So it just becomes 8/3. And so what we have here is that, in fact, this integral, this double integral that we evaluated, this integral that from 0 to 2, integral from 0 to 4 of x squared e to the minus y dy dx. Well, on the inside of this integral, you'll notice that you have an x squared, but we're integrating dy. So the x squared has nothing to do with the dy. So we can kind of pull the x squared out. And so what happens here is we really get the integral from 0 to 2 x squared, integral from 0 to 4 e to the minus y dy dx. Okay, but then the integral of e to the minus y dy, well, from 0 to 4, that's just a constant. And so that can be pulled out of the x integral. So what we really have is the integral from 0 to 2 of x squared dx times the integral from 0 to 4 of e to the minus y dy. And you'll notice that's exactly what we got. We got the integral of x squared dx, which was 8/3. And then the integral of e to the minus y was 1 minus e to the minus 4. And then we have that product. So that's exactly the result that we got. Okay, so this is another theorem that I essentially have demonstrated for you with the example. And that's if f of xy is a function of x times a function of y. Then we can look at the integral from a to b and c to d of g of x h of y dy dx as really just the integral from a to b of g of x dx times the integral from c to d of h of y dy. And that is a very helpful fact to use when evaluating these double integrals.